So my talk is When Bits Hit the TurboFan. I'm a software engineer and a developer advocate at Dynatrace. I'm interested in compilers, and that's what we're going to talk about today, but also everything else, software internals, and also specifically debuggers, which is what I've been doing for the past almost 3 years, which is what led me to compilers and to this talk. So let's begin, if we can. Opa, okay. Okay, so who knows what V8 is? No? Yeah? Okay, cool. So V8 is the engine, is a JavaScript engine, and it runs in Node, which is why I'm here, but it also runs in Chrome, and you've probably run it today. It runs in Dino, if you run that. It's pretty popular. It works really well. And so what it does is gets JavaScript and runs it. It's being developed by Google. It's existed for years, and it works really, really well. And V8 is made up of 3 parts. Before 2021. We'll also talk about what happens after 2021, but this is the interesting part. So it had 3 parts: the parser, the ignition, and TurboFan. Now the parser creates AST, and AST is an abstract syntax tree, which basically means it takes the code that we've written, and for every word or token, it just says what that means, and it gives it a bit more context, and it puts it in some sort of data structure. So for instance, for this function, it's created this AST where we have that add identifier for the function declaration that has params, which are A and B. It has a body. In that body, it has a return statement. In that return statement, it has a binary expression. On the left, we have A. On the right, we have B. And this is our AST. So this is our abstract syntax tree. When the next steps come, this is what they're going to use to make sense of our program. So that's the first part. Pretty simple. Next, we have ignition. And ignition is a JavaScript interpreter. So it takes that code, and then it takes the AST from parser, and it turns it into instructions. And these instructions are JavaScript bytecode. And after creating these instructions, the ignition interpreter runs it instruction by instruction. So it's not machine code. It's not running natively on your machine. Ignition runs it itself. And for this simple function, it created 3 instructions, and we can actually kind of read them. The first instruction loads B. Then it'll add A and B, and then it'll return that value. So pretty straightforward. It's usually not like this. It's usually more complex, and usually we can't read it. Otherwise, we would also be able to write it, and then we wouldn't have JavaScript. We just have this. So that's ignition. Now, I'll pause here, and I'll talk about something different, which is intermediate representation, or IR. Now, IR is either a data structure or code. We've just seen 2 different types of IR, because AST, the tree, is one type, and then the code that ignition produces is another type. It's used usually by a compiler, and the reason a compiler uses it is because using IR, it's usually easier to optimize our code. So a compiler's main function, a good compiler will optimize your code a lot. It would make it run faster, right? If you have a good compiler, it'll run faster. So by using some sort of IR, the compiler's job is easier. So for instance, if it had to go over every single word you wrote in your code every single time it wanted to understand what your code does, it would take much more time than using AST or JavaScript bytecode. So those are 2 types of IR. And it represents source code accurately, so there's no loss of data. Everything in your code will be in that IR. So once again, 2 different types of IR that we already saw, AST and instructions. So ignition is a JavaScript interpreter. That's how I called it. But then again, maybe it's a compiler, right? Because it takes JavaScript code and it compiles it into JavaScript bytecode. But then it also runs that bytecode. So maybe it's a virtual machine that runs JavaScript bytecode. It kind of can be all of these. But the most important thing to know is that ignition is a fast way to execute code slowly. What that means is that ignition runs fast. Ignition is not a lot of code. It is a lot of code, but not a lot of code. It's pretty straightforward what it does. And so it runs fast, but then the code that it runs, it doesn't do too many optimizations, so the code itself is going to be quite slow. So along came Google and said, OK, well, this isn't good enough. OK, this isn't good enough. We also need a slow way to execute fastly, or quickly. And a slow way to execute fastly means we need maybe something that'll run a bit slower than Ignition, but the code that it'll produce will be faster than what Ignition does. And so before TurboFan, they had Crankshaft, which did the same thing but in a different way. TurboFan's input is JavaScript bytecode, and the output is machine code. So note that Ignition creates the bytecode, and then it passes it to TurboFan. And TurboFan, what it does is optimizes the code. It makes your code run faster. But the thing is that TurboFan runs slow. And TurboFan is a just-in-time compiler, which means it runs while your code is running, right? You've never pre-compiled JavaScript. That doesn't really happen. So TurboFan will run as your code is running, which means it takes up CPU, it takes up resources, it takes time to do what it does. And you want it to not interfere with how your program is running. So while we do want to optimize the code, we can't be optimizing all the code. So what's going to happen is Ignition is going to say, Ignition runs all the code, right? When you start your program, from the moment the first line is executed, that's Ignition doing it. And so Ignition can create statistics. And using these statistics, it can tell when a function is being run a lot, or what we call a hotspot. So a function is being run a lot. If it's being run a lot, it goes and tells TurboFan, compile this, optimize this, and then we get fast functions for functions that are run often. Now, the way TurboFan does this is it creates optimistic assumptions, which means that Ignition can collect type feedback. It can tell that a function is being run with a certain parameter. And we'll look at this example where we have this function add. Now, let's say I call it with 2 numbers. Great, Ignition runs it. Pretty good. Then I'll call it again with 2 numbers. I'll call it again with 2 numbers. The 4th time I call it with 2 numbers, Ignition will say, OK, I want to optimize that. And it'll tell TurboFan, every time add has been called, it's been with 2 numbers. So TurboFan will optimize it with that assumption in mind. So it makes that assumption. Now, let's say I run it again. Now add is super fast because TurboFan optimized it, and it's working great. And I called it again with 2 numbers. Once again, great. But then I called it with 2 strings. And what's going to happen here is that we made a wrong assumption, because add is no longer being called with numbers, it's being called with strings. And so the optimized code is no longer valid, it'll be discarded, and TurboFan will give Ignition the code to run again. So basically we have this loop of optimization where Ignition gives TurboFan the code, and then de-optimization where TurboFan gives the code back to Ignition. Now, that's how TurboFan runs. That's how V8 worked before 2021. And we're going to talk about what we all came here for, which is TurboFan itself and how does it work. So this is taken from Wikipedia. TurboFan uses a technique called sea of nodes. Sea of nodes is a graph representation and a lot of other words, which basically what we need to know is what is single static assignment, what is a control flow graph, and what is a data flow graph. And once we know these, we'll be able to build our own TurboFan. Kind of. So first of all, we have single static assignment. And single static assignment is a form. So it's basically one pretty simple rule. And the rule is a variable will never change. A variable is defined once, and that's it. Now, obviously, the code that we write never goes by this rule, right? We have variables, and as they do, they change. And that's what makes us write good code. So what's going to happen is we're just going to rename the variable every time we assign to it. So for instance, for this code, on the first line, we're going to turn A into A0. We're just going to rename it. And on the third line, we're going to turn A into A1. Pretty simple, pretty straightforward. And that's it. This is single static assignment. This code is in that form. Great. And even from this simple rule, this will actually help the compiler optimize easier. What that means is, I'll give you a different example, where we have these 3 lines. And in the middle, you might see that line 3 is missing, and I'm going to give us 2 options. So one option is that we do nothing in line 3, and the other option is that we assign to A on line 3. Now, on the option where we do nothing, this is going to be the SSA, right? So we have A0, B0, and C0. And you might notice that the calculation A0 plus 1 happens twice, right? And doing a calculation twice is not optimal. We want to avoid that as much as possible. And because we can clearly see that that's the same exact calculation, the compiler can just do it once and use that same result for both lines. So we've already optimized this code. What happens on the other side is a bit different. What happens on the other side is that we've actually created A1. So we can clearly see that they're not the same, and we know not to do that optimization. So we can clearly see here how just having that form, that SSA form, makes our code easier to optimize. Now I'm going to give you a bit of a more difficult situation. Let's say we have this code, and we'll turn it into SSA. So first of all, we'll turn that A into A0. It came from somewhere. It doesn't really matter where. We'll just call it A0 for now. On the first assignment, we'll set it to A1. On the second assignment, we'll set it to A2. And then we want to log it. But the problem is that we go to log it, and we don't know if it's going to be A1 or A2, right? Because we had a branch there. We don't know where we came from. So let's solve this with SSA. Now, first of all, we're going to kind of map out the flow of our function. So first of all, we have this if. If it's true, we're going to assign 2. If it's false, we're going to assign 4. And then this is the big question of what do we do here. For this, there's a special function called phi in SSA. And phi is used when different values can be assigned depending on which node we came from. So in this case, it could be either A1 if we came from the true branch, or A2 if we came from the false branch. And what we're going to do is create a whole other variable. And in that variable, which is, again, only assigned to once, we're going to say it's either A1 or A2. We can't know at compile time which one it is, but it doesn't really matter. And so we're going to create a new variable and specify what the value options are. So if we take this whole thing into consideration, it's going to look like this, where we use A3 after that branch is over. So that's single static assignment. That's all there is to it. It's quite simple because there's only one rule and one function, but it's a good thing that computers do it for us because doing it as humans is not that fun. Now, the next thing we need to know is what is a control flow graph. And luckily, we've already built a control flow graph here. We didn't even know it. But if we remove the instructions, this is actually exactly the flow of our program. So a control flow graph is built up of basic blocks, which are consecutive instructions. And the most important thing is that they are consecutive. So no matter what, they'll always run one after another. Now, in this case, we have 3 basic blocks because the first 2 let statements are always going to run one after the other. That while statement is going to run on every loop, right? But after it, it could either go into the while or end the while, depending on if the condition is true or false. And then, once again, these 2 are going to run consecutively, so they're a basic block. This control flow graph will show us control dependencies, which could be if, while, for, a function, a call, a return, just basically whenever our code branches out and changes the flow of it. And most importantly, it doesn't care about data. It's only about the flow. That's why I removed the instructions when I showed you the graph earlier. Even just a control flow graph will help us optimize our code. And we can see this. Sorry. Let's show another example first with this function. First of all, because it's a function, we're going to start at the start. We're going to have this be a basic block because they always run one after the other. For the while, this is how our nodes are going to look, right? If it's true, we enter the while and then loop back. If it's false, we end the while and go to the next node. And this is our condition. When it's true, we're going to execute what's in there. And when it's false, we're just going to jump to return sum. And that's it. That's the end of our function. Right? Cool. So this is our control flow graph. Now, even with just this, we can see how we can optimize our code easily. Because let's say this is our graph, and we can see that it kind of like loops around, goes back in all sorts of directions. But there's one specific node that doesn't have an arrow pointing towards it, right? Which means that we'll never, ever get to that node. Which means that we can remove it. And removing code is good. Removing code means we have less code to run, which means our code is smaller and more optimal. So this is an example of dead code elimination where we can just remove code that we're not using. If you run like a linter on your code and it like shows you a squiggly line and says, hey, this function isn't used, it's doing this probably behind the scenes. So that's signal static assignment and control flow graph. And the last thing we need to know is what is a data flow graph. And the data flow graph, if I may say so, is probably the simplest one of the three, because it just basically shows how my data changes throughout the program. So it'll show the operations as nodes and the data as edges. So let's say here we have the first operation is going to be that multiplication, and inside goes A, inside goes 2, outside goes B. On the next line, we'll take that B, we'll add it to A, and outside goes C. Pretty straightforward. We can do this with the same code we had earlier. Now, there's no operations except for in that while loop, so we'll just focus on that. In that while loop, this may be a bit confusing or surprising, but we actually have two operations here. The first operation is going to be length, right? Because that's an operation we do on data. And the result is also data. So it needs to be in our data flow graph. Now, after we get the length, we're going to compare it to I. Once again, an operation on data. It's going to be in our graph. We'll split this into lines just to make it easier. In this line, once again, we have two operations. The first is going to be to load the ith element of R. The next one is going to be to add sum to it. And then it's going to put the result in sum as well. And in the last line, that same thing. I plus 1 equals I. So that's the data flow graph. We can kind of merge this together. If we had turned the code into SSA form before we did this, we could have done it easier. But that's basically all you need to know. Now, CF nodes is taking these three and putting them together. So what's going to happen is we have our control flow graph and our data flow graph in the same graph. So we have one graph showing both. And it's going to be an SSA. Most compilers nowadays use SSA, so this is not surprising. But something that the CF nodes does that a control flow graph doesn't regularly do is not use these basic blocks that we were talking about, but actually split it up. So it's going to look at every single instruction and going to say the control dependencies between each and every instruction. So it's a bit more granular than a regular control flow graph. Now, this is an example of a sea of nodes. As you can see, it is, as it says, a sea of nodes. This is the sea of nodes, by the way, for that calc sum function we were looking at earlier. So I'm not going to go over it, but what you need to know is that we have these dash dependencies, which are the control flow dependencies, and the full dependencies, where the arrows are full, are data flow dependencies. And what's interesting about this, and what we can already see, is this specific part. Sorry for the pixelated image, but this part is where we call r.length. In our code, we had r.length, and this is in the graph. And what's interesting is that there's no dashed arrows to or from the load array length node, right? And the dashed arrows meant control dependencies, which means that load array length has no control dependencies. Now, we can clearly see this in our code, right? Because R doesn't change, right? We don't change the array at any point, especially not in the loop. We could just take that calculation outside of the loop. Now, in the previous situation, what happened was we were doing that r.length operation every single time the loop restarted. Okay? So every single iteration of the loop, we were doing this calculation. Not optimal, not good, no reason to do that when r isn't changing. But after, we have only one operation. We do it before we start the loop, and we don't have to repeat that again. And because we have no dashed lines here, that's how the compiler knows, okay, there's no control dependencies, which means it doesn't matter where in the loop this calculation goes, and so I can move it outside of it. So in general, sea of nodes allows less compiler passes. Basically what happens every time our compiler uses IR, remember? So every compiler creates different IR. And once it's created that IR, it'll do multiple passes. So it'll go over all of your code or all of your function, whatever it's focusing on, a few times. And every time it'll optimize it more. Sometimes it needs to restart the pass to optimize it again and again for different optimization types. But this, because of the granularity and because of how this is represented, it allows for less compiler passes, so it's faster. It also removes unnecessary dependencies. Remember when we said that it doesn't look at basic blocks, but it looks at every single instruction? That means that it can look at dependencies on a more granular level and look at these specific instructions and move them around much easier. And in general, it'll just be more, it'll help move instructions around because we're looking at every single instruction and there's an order in the graph, and so it'll be easy to move them around and keep the integrity of our code, make sure our code is doing the same thing. On the other hand, it's not very cache friendly, and in general, it's slow. It's slow to create this kind of graph. Like, it wouldn't be easy for us to create this kind of graph, so for the computer, it isn't really easy as well. And that's why it takes time. That's why we called it a slow way to run code fastly. Now, I do want to leave you with some practical tips. So you can go to your employer and tell them, this is everything I learned at Node.TLV. It was really helpful. So first of all, be consistent with the types you pass to functions. This will avoid de-optimization. Now, the best thing we can do when we're talking about TurboFan and making sure our code is optimal and that it's making our code optimal is to make sure there's no de-optimization. And de-optimization happens when types aren't consistent. So if we are consistent with the type we pass to functions, there's no reason for TurboFan to de-optimize our function. We're always going to want to declare properties on the constructor. Again, this is the same reason, because if we declare properties after our constructor, so we've created an object and then we do object.a equals something where a didn't exist before, we're creating a new type. And once again, TurboFan will need to de-optimize if we do that. I don't know if anyone does it, but don't declare classes inside functions because it's going to create a different type every single time you call that function. So very bad idea. Avoid arrays with holes. Once again, not a very popular thing to do, but make sure you don't do it because it'll have to realize that it makes it much more complicated for TurboFan to understand what the type is, and it has to kind of go up in the, propagate the prototype chain. It takes time, and it causes de-optimization, so it's not good. So don't do that. Just insert undefined between index 0 and index 5 here, and that'll be much better. And this isn't really a tip, but don't be afraid to use built-ins because you may think that, for instance, for each will run slower than actually splitting up your loop. But as we saw in our example, it doesn't. TurboFan knows to do the optimizations that you might do in your code manually. It's not really necessary. And specifically for built-ins, I wanted to say this because they work specifically on optimizing built-ins. So they look at the performance of every single built-in in JavaScript in Node, and they optimized it using TurboFan. So don't be afraid. Use them. If it'll make your code clearer, better, easier to read, use them. These are all general tips. It's not like you must do this no matter what. It's general tips. You should do it if you have a reason not to. It's probably not going to cost you that much unless you do it on every single line of your code. So, as I promised, these are V8's 3 parts before 2021. TurboFan, for instance, was introduced in 2018 or late 2017. And then in 2021, they came around and they said, well, Ignition runs fast, but the code is slow. TurboFan runs slow, but the code is fast. We need something in the middle. And so they created Sparkplug, which is a non-optimizing JavaScript bytecode compiler. Which means that it doesn't do those compiler passes that we were talking about. It doesn't do the aggressive optimizations that TurboFan does. And because it doesn't do that, it's much faster, but the code is slower than what it would be with TurboFan. So it's in the middle there. And then, in 2023, they came around and said, wait, Sparkplug creates code that's too slow. TurboFan creates code fast, but the but TurboFan itself is too slow. We need something in the middle again. And so they created maglev, which is a simple SSA compiler. And by this point, we all know what SSA is. So it doesn't use sea of nodes. Sea of nodes is like extreme on the aggressiveness of compilers scale, which means that it optimizes a lot. It makes a lot of assumptions, and then it optimizes a lot. Maglev makes assumptions. It's not like Sparkplug where no assumptions are made. But it makes less assumptions, and so it de-optimizes less, but it also optimizes less. So it optimizes, the optimizations are less, but then it also isn't wrong a lot, so it doesn't have to be de-optimized a lot. So this is kind of the order where Ignition will run fastest, but create the slowest code. TurboFan will run slowest, but create the fastest code. And depending just on how often your code is run, it'll go from Ignition to Sparkplug to maglev to TurboFan. Now, that's all I have to say about TurboFan and V8. Thanks for coming. Thanks. This is a link to these slides. They're good because I also have a bunch of resources if you want to read more. Sea of Nodes is pretty cool. Some guy named Cliff Click made it up in like 1980-something. And it's used by Java. Java also has compilers in it, so it's used by the most aggressive Java compiler. It's used by the most aggressive JavaScript compiler. And I recommend some cool stuff. Thanks.